one more video. This one's extra credit should you choose to do the questions for it. Otherwise, just enjoy and learn, I hope. In any case, we were talking about light, and I love light. In fact, when I was a kid, I used to have my dresser drawers had 5 drawers. Top 2 drawers were clothes. Next 2 drawers were toilet paper and paper towel tubes. The bottom drawer, lenses. These particular ones aren't from my original collection, but I used to play with these things all the time, make all kind of telescopes and microscopes and rangefinders, and just look through them and burn stuff. Did burn ants one time, and the smoke went up in my nose, and I felt terrible, and I've never done that since. But what you missed, I forget if I got to do it any day. Burn melt pennies with the giant Fresnel lens I have at school. Lots of neat stuff. Let me show you a couple things about lenses. I'm not going to try to do ray tracing diagrams and stuff that I certainly could and I have in other years. But right now, I'm going to just show you a couple things. 2 basic kinds of lenses. The kinds that are fatter in the middle, called convex, and the kinds that are skinnier in the middle, called concave. Well, convex lenses, ooh, that marker ain't going to do, is it? Maybe this will. Convex lenses have this way of bringing light rays together to a focal point. Concave lenses have this way of spreading rays apart. I am not going to go through my usual spiel of how that results in image formation. It's a terribly practical thing, tells you how a lot of common things work, including glasses and contacts and magnifying glasses and projectors and this camera right here that's taking the picture on me. It's forming a real image on some little chip. But let me just show you a couple things I can do. So like here's this convex lens. What kind of neat tricks has it got? Well, one thing it can do, it can bring rays from that lamp together. Oh my gosh, it's a lamp. Oh, weird. It's a mysterious ghostly lamp floating right there on the screen. Some kind of hologram? No, it's just an image. You do this. This is happening on the back of your eye, on your retina. Your lens of your eye is focusing light, making an image. And notice it's got to be focused, right? See if I change the distance by the way the light is. Of course, that one right there. Maybe seen it in another video. Now, what do things look like through it? Well, far away, things like that lamp over there just look like little upside down lamps. Maybe you can see that. The whole world's upside down over there. Maybe you can see. But if I get it too close, well, I'm trying to do this right here. Let's see if I can aim right. Whoa, where's things at? Maybe I'm blocking the view. It's hard to aim. Anyway, boom, and then everything's just kind of blurry and right side up. Now you're looking through the lens. I'm glad I thought of this. Now you get to look through it at stuff. Here stuff's just kind of big and right side up. And then when I do this, it turns small and upside down, and so can I. I can't see this too well. Maybe you can. There, I don't know what you just saw. I'm probably small and upside down, at least my head is. And now, whoa. Ooh, got strange, weird colors in there. That's bizarre. I like that. Well, anyway, so convex lenses can make what's called a real image on a surface like that or floating in the air. Or you can make a virtual image, a great big right side up virtual image. But then there's concave lenses. What tricks can they do? They spread rays out and they make me look small. Wow, the whole thing looks small there. But you know what? All they do is make things look small. They don't do any weird flip over tricks. They just make things look different amounts of small. There's a use for these things too. They not only make things small, they make things look close. I know that sounds ironic, but it's true. And it's how contacts and glasses work for nearsighted people. Nearsighted people need these concave lenses. Farsighted people need these convex lenses. Oh, other things I wish I could have shown you. I'll tell you one. This is too bad. I can't really set this up in here. I don't think I brought it home. Don't believe I did. But with a laser, a special thing, this thing called a hologram. You've probably heard of holograms. You've probably seen, like, supposedly holograms are like these, like they're not there, but they look like they're there. Well, that's kind of true. There's a hologram I would have shown you if you'd been here. Let me describe it to you. The description is nowhere near good as being here and seeing the real thing. But basically it goes like this. I have this piece of glass. I did not bring it home. No, I did not bring home a hologram. I don't think. And I probably couldn't show it to you very well anyway. But anyway, I have this hologram. It's this piece of glass. It's about this big. It just looks like a slightly smudgy piece of glass. You don't see anything on it. You don't see anything through it other than it's just kind of like fingerprinted up looking kind of glass. But when you shine expanded laser light on it, I'm careful with the way I do the light so nobody gets too much laser in their eyes or whatever. But anyway, when I expand the laser light out and you look at it, you don't see anything on it, you see something through it. And with this particular hologram, you see a digital phone. It's from probably 20, 30 years ago, but it's a digital phone with little push button things and a magnifying glass. The bizarre thing is it's not just a picture of a phone in a magnifying glass. It's like floating out there just beyond the hologram, like about this far behind it. And I've had students be kind of like shocked when they see it. In fact, sometimes they look and literally look around and say things like, "Where is it?" Like they're looking for the thing, like they saw it floating there in front of them. And the magnifying glass in the hologram works. I'm going to tell you really quickly kind of how a hologram works, just real fast, just so I can say I said it. Let's take a quick look. Here's how you basically make a hologram. Then I'll erase my lenses right quick. And then I'm going to go on with some other neat stuff. I'll try to not talk more than half an hour or so, but remember, you can ask some questions if you want the extra credit. So in any case, here's basically how you make a hologram. Oops, squeaky. You take your laser, and the laser shoots out light waves, and it's expanded with some lenses, and it's all safe and everything. So here come these light waves coming out. Now here is like the person you want to make a hologram of, you know, doing whatever it is people do when they get holograms made of them. Now, when the wavefronts hit the person, they reflect off, and they come off in some weird, complicated way. I'm not even beginning to assume that I've drawn those correctly, but the wavefronts are all distorted and weird and everything. And then here's your eye. You're looking at the person with the laser light shining on them, and you just see a person. You know, the light comes in your eye, gets focused on your retina back there, and your brain, you know, here's a cutaway, there's your brain. Okay, interprets it, and you see a person. I'm not going to go into the image formation thing. It's just like when these weird wavefronts hit your eye, your brain sees a person out there. Now, to make a hologram, what you do is instead of putting a person there, you put a piece of film, basically photographic plate. Now, most pictures these days are made on these little chips, you know, semiconductor. I don't even know quite how they work. I need to look that up more sometime. But anyway, so if these waves, just like I'm showing, fall on this photographic plate, it ain't going to look like nothing. It's just going to be exposed, just flat, grayish looking. You'll just be, once you develop it, it's just like a sort of dimmer piece of glass. It doesn't really do anything. And there's no picture in it or anything. The information is utterly lost. But what you do is if you take a semi-transparent mirror, and by that I mean a mirror that lets through about half the light and reflects about half the light. If you do that, some of these original waves will go down and hit the photographic plate. They themselves wouldn't make anything the least bit interesting. Neither would these other waves coming from our little subject out here. Some of those got through there too. I guess we could go around. But when they hit at the same time, there are places where, you know, this wave combines constructively with the other one, you know, crest on a crest, so to speak, of these electromagnetic waves, and it'll expose the film there. There'll be brightness and it'll expose the film. In other places, there's destructive interference, and then other places, constructive. It is an absolute mess, an unintelligible, complete mess. If anything, it looks like a bunch of stripes and fingerprints. It doesn't remotely look like this person. This is basically what the photographic plate might look like, you know, just a bunch of like little topo map, little patterns and stuff. And you'd never guess that was a person. But here's the deal. If you now shine a laser through that thing, I'll kind of draw it at an angle. It's got all the funny little things all over it. In fact, you know what? I might just put the laser up here. Okay, so here you put your photographic plate there that's got the funny smudgy stuff all over it that doesn't make any sense at all. And you take your laser and you shoot your laser waves at it. They will diffract through the clear places, between the dark places. And those diffracted waves will interfere in some terribly complex way that will unscramble the bizarre, unintelligible complexity of this thing and produce these waveforms that are identical to the ones that you would have had in the first place, recreating in full 3D action. Action I'll talk about in a minute, but recreating in full 3D the person floating out there. And again, it's weird, and I wish I could show you. You might have seen some holograms before, but not usually these good ones. Let me tell you another hologram I got to see one time. I saw this back in the early 80s. I tried to buy one like it. It's terribly hard to find, and I found it's sort of a poor facsimile of it that I actually bought in the school. It has some more, but it didn't work very well. This thing, actually, I tell you, was called the Kiss. I'll tell you what it looked like. It was like this. There was this hologram. You didn't even need a laser. You put this it was, I'll even tell you what you call this kind of hologram in case some interested soul wants to look it up. So here's the deal. There was this can that was really just a piece of poster board, literally a poster wrapped up into a cylinder with a little window cut in it. And there was a piece of plastic taped into the window, like just a little window in your little castle or something. And there was a simple, actual, just light bulb in there. I mean, an incandescent light bulb, not even a laser. And when you stood out here, say, for example, and looked, that's your eyes, and looked, you saw a girl in there. And when you see her head floating in there, her head's just floating in the can. And you see her looking like this way. And she's just hovering. If you start to walk around the thing, she kind of like looks over at you. I mean, not just like, I think her eyes are following me, but I mean, really, her head turns and she looks at you. And then as you continue to walk, she starts to smile. When you get to about here, out here, looking straight in, she's looking right at you. You see her hands start to come up. Then somewhere over here, she puts her hand to her mouth. You keep walking. She blows you a kiss. And then she looks back straight out again, off into the distance. And if you keep walking, she looks over at you one more time and winks. If you walk backwards, she'll wink, suck the kiss back in, and follow you, and then look back this way again. It was bizarre. I actually used that the first year I taught physics at Fayette County High School. I was able to borrow that hologram from Georgia Tech, where I'd been when I saw it, to try to drum up interest in physics. It was pretty amazing. But in any case, so there's a whole world of, and by the way, a hologram, if you break it, the whole image is still in every piece. You can't like cut your old significant other out of the picture. They're everywhere in the whole thing hologram. Holographic stuff is interesting, whether or not there's holographic information encoded in the universe. You can look up holographic universe stuff and read weird things. By the way, that particular hologram, it was called the KISS, but it was a multiplex hologram. It's one where they actually get motion in it that is reflected when you move, and then there's like a motion picture. There's really a bunch of holograms stuck together. It's really amazing. It's a white hologram. Okay, you see there's just all kind of neat stuff to learn about that. But what I'm going to do now, let me branch off this thing about light. I said it was an electromagnetic wave. I told you that James Clerk Maxwell in 1865 predicted electromagnetic waves. They turned out to be true. I got to tell you, this was an enormous coup in physics, so to speak. I mean, this was just like, oh, wow, we have got the world figured out now. Physicists thought basically that they had the whole universe explained. They were really kind of big-headed about it along about 1880, 1890. There were a few little mopping up details to be done. Maybe there was a few little things they didn't understand off in little corners of knowledge. But there was this haughty sense of accomplishment, like we've just about got it figured out. There's not really that much for physicists to do anymore, except that there were some looming, lurking problems. And they came in a couple of different kinds that led to two dramatic revolutions in physics that have left us baffled to this day in some ways, and yet enlightened greatly. Enlightens light. One thing is, the light was supposed to be this electromagnetic wave, and I've already told you it ended up having particle properties. I'll get back to that in a second. But light was supposed to be this electromagnetic wave. But what was the medium for its transmission? Well, you know, it might be air or glass or whatever it's going through, but no, it gets here from the sun, and there's no air to speak of in space. How does it get here? They actually invented something called, listen to this name, the luminiferous light-bearing ether. It was supposed to be the medium for the transmission of light. And if you were taking physics 130 years ago, 1890 or something, you'd be learning all about the ether and its mysterious properties, how it's like no resistance, there's no friction or anything as you go through it. It doesn't do anything except it's like a billion times as rigid as steel. At the same time, ooh, how can that be? And some kid in the back of the class is going, yeah, right. And the teacher is saying, well, you better know it for the test, you know, because that's what they believe. Turns out, ain't no such thing. I won't go into the details of how they found out, but well, I'll tell you that some guys named Michelson and Morley in 1883 tried to make an ether speedometer to measure the speed the Earth was going through the ether, and they got zero. They got zero no matter where they were in orbit around the sun. Unless you wanted to go back to believing in a geocentric universe, that's a thought, but that's not where it went. You have to believe there's no ether. And if there's no ether, then nobody can be the one to say what light's moving through, and there's no medium, and everybody's going to have the same speed of light, and that causes some weirdness. I am not going to go into the weirdness here except to say a couple of thought-provoking examples, and I will refer you, if you're interested, on this same YouTube channel. I made these videos for AP Physics, or AP Physics C. It's AP Vid 7, 10, and 12. Some of it's a little beyond, you know, it was aimed more at the AP class and took off on a couple of things they already knew from studying electricity and magnetism. But to a large extent, it is accessible. You might want to give it a shot. Let me just tell you a couple of weird things. There's the one about that's called the twin paradox, where you and your identical twin, saying your 20th birthday, one of you decides to fly off to Arcturus, a distant star 40 light years away, and you fly off at 99.99999999% the speed of light. And you fly to it. It's 40 light years away. It should take about 40 years at practically the speed of light. So you spend like 40 years, according to whoever stays home. Say you stay home. You wait for your twin for 40 years they just got there. You wait for 80 years. You're 100 years old. And they come back. Finally, they're home. They flew out there at almost the speed of light. There was nothing to see, so they flew back at almost the speed of light. And they get home 80 years and a few seconds or minutes later, and you're 100 years old. And they step off the spaceship, and with all the numbers I said, your identical twin is still 20 years old. In fact, has only aged 4 days in the last 80 years. Sounds like science fiction. It's real stuff. We don't fly that fast, not humans anyway. Well, subatomic particles we do this with, and they have lives of their own, and they've been extended that way. But as far as like a full-fledged, full-grown human being flying off and coming back and doing that, we haven't really done that. But we've experimented in other ways. This stuff's true. I really believe it. See, not even crossing my fingers. Not even holding a marker. And I can explain it. And you can watch those videos and see it. It's weird, weird stuff. It also shows that time is passing slower. Well, this is an extension called general relativity. Time is passing slower here downstairs than it is upstairs. Just barely, barely, barely. But it's true. It's real. It's baffling. Anyway, let me just write down the names of these things in case you ever want to learn about them. In 1905, okay, luminiferous ether. No such thing. In 1905, Einstein, that guy, came up with this special relativity. It's Einstein, the Albert guy, the guy that my niece's husband's mother went trick-or-treating at his house in Princeton, New Jersey. Yep, I might have told that. I got a name drop a little bit, right? So anyway, special relativity, all this bizarre stuff about the speed of light. Light's kind of essential in this universe, it seems. And then in 1916, he expanded it with something called general relativity, which is the whole thing about like gravitation being a curvature of space-time and all that weird stuff, warped space and weird, bizarre, funnily black hole things and all that amazing stuff. The sun bends light around it. Time is slowed down by intense gravitational fields. All that. And that is, again, this whole relativity thing. Now, that still treats reality in surprisingly conventional terms. It's actually still called classical physics. It's not utterly breaking the rules of the way reality is structured, something else does. So, about the same time as this was going on, very simultaneous with it, another revolution was brewing. I won't go into all the details of it, but I'll mention a couple of things maybe. One is I told you about my son's airsoft BBs that would not be lit up by intense red or intense green light, but faint blue light would light them up great, because it turns out light is a particle. So there was this weird particle type nature to light, and we call this wave particle duality. I talked about this a little bit in another video and maybe even live with you, and even asked one question on the last test about it. It's a hard to grasp thing. I don't expect you to grasp it. I barely got it myself. And I mean, depends on what you mean by grasp. I got a good feel for it, but doesn't mean it really makes a whole heck of a lot of sense to me. But anyway, the idea that light can be both a particle and a wave at the same time, well, depending on what you do, you look at it and try to measure a wavelength, it's got one. You measure momentum, it's got one. So the question is, how can it be these things? Well, that's one of the looming things. But here's another weird thing. I'll tell you something. How about this? How about the non-decay of atoms? Let me tell you what should classically happen. According to everything, even relativity, everything, Newton, Einstein, all those smart people, Maxwell, all those smart people would have had to have told you that the following should happen with atoms. With an atom, you should have like the proton in the middle and you got an electron going around it. And it turns out that accelerating charges generates electromagnetic radiation, light, and the light should leave and take with it some of the electron's orbital energy. And theoretically, to use that term, according to all the theories before, theoretically, the electron should quickly spiral into the nucleus of the atom and make it not be an atom anymore. All there would be neutron everywhere, just neutrons. There would be no people, no worlds, no light. I don't think there'd be light. Maybe there'd be some light when it first happened, but not after that. Probably all go dark and just be a bunch of neutrons, and we would not exist. And so this is not what happens. In fact, what happens, as you know very well, is the electron continues to orbit the atom. It doesn't give off the light it should be giving off unless it suddenly changes to a different orbit and then gives off the light in a very definite chunk of change called a photon. It's a wave and it's a particle, but it's a very specific amount or quantity, and that's why this is the birth of what's called quantum mechanics. It's this whole realm of stuff. I'm just going to try to expose you to it a little bit as best I can in a few minutes. But anyway, quantum mechanics says that the world comes in little bits of exact change and not in between amounts. You know how money is? You can't like spend 57.34 cents for something. It's either 57 cents or 58 cents. If you didn't even have pennies, you probably couldn't do that. It's saying that the world only comes in definite chunks or bits, not continuous amounts of energy, of light, maybe even, possibly even of time. Not so sure on that one. I'll hold off on that. But in any case, quantum mechanics has some weird stuff to say. I'm only going to touch on it. One thing I'm going to say right now is that one way of understanding why electrons can only orbit in certain levels is because when they are in the atom, They're better thought of, not as orbiting particles like you classically want to think. They're better thought of as harmonics, standing waves. Now, I'm not saying they look like this or travel this path. That's a very schematic, metaphorical representation here. But basically, they exist as notes. Yeah, the energy levels of atoms are analogous to notes, musical notes in a way. And just like a guitar string can only make certain harmonics, an atom can only have certain energy levels, and the changes between them are abrupt and very definite amounts that exhibit as particles. It's weird. Let me show you another weird thing. Another weird thing is that things that we thought were particles, like, oh, I just kind of said it. It's not just that light that we thought was a wave turns out to be a particle. It turns out that particles are also waves. It's even possible to calculate the wavelength of, like, if I threw this marker at you, the marker would have a wavelength. In theory, the marker would diffract going through some opening. Now, you'd have a heck of a time ever trying to see this diffraction pattern in the case of a marker going through an opening this wide. It turns out the wavelength is absurdly short, and the nodes and antinodes are so close together that it stays in one piece as a marker. But let me show you what happens with electrons. If you shoot like, say, how about this? If you shoot an electron through a slit, it goes and hits a wall somewhere, some detector, some photographic plate, or some detector that detects electrons. Now, actually, it may hit in different places. Sometimes it hits here, 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 here. Well, it's weird. Even if you shoot it in the same direction every time, it hits in different places. And then there's places where it never hits, and then there's other places where it does again. And then there's other places where it never hits, and other places where it does. You actually get diffraction. This is as if, I'm not saying this happens with a baseball being thrown through a door, through an open door, but it's like if I threw a baseball through an open door, like the door of the classroom, and it goes and hits the wall across the hall. What if the baseball frequently hit where I was throwing it, and often close to that? There were some places it never hit, and then other places off to the side of that where it hit sometimes, and other places it didn't, and other places it did. What the heck? That's what waves do. So the electron is showing wave properties. Here's one of the really weird things. If you have two slits and you spray electrons at it from over here somewhere, you're just shooting a mess of electrons, you would think that you would get like a bunch of hits over here and a bunch of hits here, because the ones that went through here hit that one, the ones that went through here did that. That is not what happens. Instead, you get this bizarre pattern. I'll just indicate it as like a graph of intensities of where it hits. The biggest, most popular place to hit, one of them is straight there where they can't possibly go because it should be a shadow there, but they go there anyway. And then there are places that never hits, even though they're in the line of sight, and others they do, and others they don't. And then you go, what the heck is going on? I just shot electrons through there and they're hitting all these crazy places. I'm going to get a better look at this. And if you try to watch, this is the sneaky weird thing about it. First of all, you would rightly ask the question, if an electron hit here, which slit did it go through? I was shooting electrons in the dark, and I know some electron hit down here. How did it get there? It's out of the way. It shouldn't be able to go there. The weird thing is, if you try to spy on it by anything that detects it in any way, like shining a light on it, like I want to see these electrons, they're flying through the dark, and I want to see them, so you shine a faint light on it. As soon as you start to shine a light on it, it gets like shy or something, and it starts to destroy the pattern. By the time you shine a bright enough light to see all the electrons go through, they will no longer do this. It's like they'll only do it in the dark. Weird. It's baffling. It's really weird. And then there's other weird things like you ought to look at, if you want to read some really weird stuff, just because you like to read weird stuff. I don't know, I do. You ought to look up, for an edgy thing, just to get on the edgy weird side about it, maybe you could look up, what's the best way to say it? Well, look up, there's somebody named Alan Aspect, and he did this stuff where you pair produce these, there's other people too, it's not just him, that's just the name I have at the bottom of my head. You pair produce these little particles, and they go off in their opposite directions, and basically they seem to be like twins separated at birth, and when you do something to one of them over here, somehow it's communicated faster than light to the other one. Maybe that's the interpretation, maybe it's not, but it's a weird correlation, some spooky action at a distance, kind of superluminal communication, non-locality, that's the weird word, non-locality. This is an idea that would suggest that, entanglement, quantum entanglement. These are fun ideas because, and they sort of get abused. I mean, they're scientific concepts, it's scientific experiments, but they're fun to play with because, they have some interesting possible implications. Quantum entanglement, it's this thing that comes up with like, well, specially rigged experiments. But what if it's the way everything is? What if like the wave function that describes me is entangled with the wave function that describes you at this very moment? Or what about if the whole universe is tied together in some kind of entangled web and we're all connected in some ethereal, weird way? That's just a hint as to how physics can be fun when you get into the metaphysical, theological, all kind of weird stuff. Frankly, it's a little bit abusive of physics, and sometimes some physicists like get a little snarky if you're doing that kind of stuff with it. Oh, there was a whole bunch of books about quantum mechanics back in the 70s and 80s, the Tao of physics and stuff like that, where people try to get all Eastern mystic-y about it and everything. I'll sort of, in a way, it's almost like I want to encourage you to look at it, and at the same time warn you that sometimes these people go off the deep end and imply things that don't need to be implied and probably aren't justified. But on the other hand, it is really weird, and nobody's ever quite made sense of it. In fact, I'll say one more thing about quantum mechanics. Like when you say want to know where an electron is, it seems it may not be anywhere, or maybe it's everywhere until you look. In the very act of looking, according to the Copenhagen interpretation of quantum mechanics, crystallizes it into a reality. Almost like the tree in the forest didn't make any sound, or did and didn't make more sound and less sound unless somebody heard it. The role of the observer is what gets interesting there. And the idea of whether or not reality is frozen in place until you or I or somebody looks. Again, one of those ideas that I'm sort of naughty for saying because, we don't have good solid evidence of how it implies anything spooky or weird, but it's fun. Look, physics dabbles in some really neat stuff, and it's always fascinated me in that way. Now, let me just say a little bit more. Quantum mechanics is bizarre, hard to wrap your head around. Get a book about it sometime. It's also a very accurate, routine, mathematical way of computing stuff, and it's very respected. It's not just some spooky thing. It's why there's matter, basically. It's the structure of the universe. But it's very hard to reconcile it with general relativity. And nobody yet has figured that out. People have worked hard on it and have inklings of ideas. But you remember how in our study of the Copernican revolution and all, it was a matter of, I hope this thing's still recording. It was a matter of